A very good afternoon to one and all. Add the opportunities, subtract the errors, multiply the victories, divide the obstacles, integrate your caliber, differentiate your weakness, inverse the destiny, simplify the struggles, and win your life. On behalf of the organizing committee of this virtual international seminar, we thank each and every good heart who made yesterday's event a memorable one and today's event into reality. The capacity to learn is a gift. Ability to learn is a skill. The willingness to learn is a choice. So with this choice, I hope there are so many participants with us today. We are in the path of learning, which is the extended real life. We are in the second day of our seminar. I'm very happy to welcome the eminent speakers, learned professors, enthusiastic scholars, and students.
One song can change a moment. One idea can change a world. One step can start a journey. But a prayer can change even the impossible. In no way different to that, let's start the occasion by seeking the blessings of the Almighty. Let us feel the presence of Almighty through the invocation by Ms. V. Deepika, 3rd BSc Mathematics.
நம்மிலுள்ள இறைவனை அனுதினம் துதிப்போம். நம்மிலுள்ள இறைவனை அனுதினம் துதிப்போம். அனைவரும் போற்றி அறிவை வளர்த்து இந்திய பண்பாட்டினை கண்களாய் கொண்டு நேர்மை வாய்மை ஒழுக்கம் ஓங்கிட நம்மில் உள்ள இறைவனை அனுதினம் துதிப்போம். அறிவு பண்பு உழைப்பு என்ற கொங்கு நாட்டின் மந்திரம் முழங்க அறிவு பண்பு உழைப்பு என்ற கொங்கு நாட்டின் மந்திரம் முழங்க பாரத நாட்டின் பல்கலைக்கழகமென பாரினிலே புகழ் ஓங்கி வளர்த்திட நம்மில் உள்ள இறைவனை அனுதினம் துதிப்போம். அனுதினம் துதிப்போம். அனுதினம் துதிப்போம்.
Thank you, Deepika, for making us showered with the blessings of God. We don't get a second chance to make a first impression. The gathering gets filled with joy and happiness when they are welcomed, and welcoming is part of a culture and heritage. I hand over this task to Dr. M. Vivek Prabhu, Organizing Secretary of this seminar. Over to you, Vivek.
Thank you so much, ma'am. First of all, it's my immense pleasure in welcoming our beloved President, Dr. M. Arisami sir, and our Secretary and Director, Dr. C. A. Vaski madam. So both of us are being a guiding force behind all our activities, and only because of their support and encouragement, all these knowledge sharing programs has become possible. So in this occasion, I just convey my heartfelt gratitude and welcome to our President as well as Secretary and Director. At this juncture, we have most eminent personalities in the field of topology, Professor Dr. Said Jafari, Dr. Akim Atman, Dr. S.S. Benchali, Dr. M. Parimula. So all these four eminent personalities in the field of topology have given consent, and they are sparing their valuable time with us, and they are about to convey their research ideas, and they're going to transform their research ideas. The budding research scientists, they are going to encourage them. So for accepting an invitation and for your valuable presence and for your lecture, we wholeheartedly thank and we welcome all the notable, knowledgeable professors over here. At this juncture, I would also like to welcome our mentor and our former principal, Dr. R. Devi. She is the guiding force, and not only for me, for almost all the faculty members in our department. So once again, I extend my welcome to Dr. Devi madam. Also, we have eminent personalities like Dr. Bala Subramaniam sir, Jnanambal Ilango ma'am, and so many other eminent professors in this occasion. I welcome one and all. At this juncture, I would extend my warm welcome to our beloved principal, Dr. M. Lakshmana Swamy sir, our Chief Executive Officer, Dr. V. Chinnu Swamy sir, our Research Dean, Dr. S. Palsamy sir, and our Dean Academics, Dr. S.R. Madan Sankar sir, and other academic staff members for their support and encouragement in all our activities. So, our head of the department, Dr. V. Gokulavani, who is the convener of this international virtual seminar, who is always supporting us and encouraging us in all these sessions. And I would also like to welcome Dr. M. Vigneshwaran sir and Dr. P. Sadish Mohan sir, who are the coordinators and organizing secretaries of this international webinar. Moreover, I would like to welcome all our other faculty members, Dr. D. Vijayalakshmi Madam, Dr. M. Vendachalam sir, Dr. C. Ravichandran sir, Dr. L. Vidyarani Madam, Dr. N. Mohanapriya Madam, and Dr. E. Prakash sir, Dr. S.P.R. Priyalada Madam, for all their support. Only because of all their support, this function is possible. So at this juncture, I would like to welcome and thank all of them for their hand-in-hand support when needed. And most importantly, I would like to thank and welcome all the participants who are here. So we have many participants from Karnataka, West Bengal, from the Kingdom of Saudi Arabia, in and around India from several parts. So we have around 250 participants over here and as well as in YouTube. So at this juncture, I would like to welcome all our participants and our beloved students. Once again, I welcome you all. Thank you so much.
Thank you, Vivek, for placing the red carpet through your welcome speech. The fragrance of love spread only in the direction of the wind, but the goodness of a person spreads in all directions. Vanakkam Hakim sir, Ahlan Biha Hakim Evatman sir. This is the first time we are having you with us and hope this relationship will continue forever.
Thank you.
Thank you, sir. It's the time to introduce the chief guest of today's session, and I hand over the job to Dr. C. Ravichandran, Assistant Professor of Mathematics.
Thank you, madam. Good afternoon to everyone. It is my honor to introduce our resource person, Professor Dr. Hakim Ahmed Athman. Dr. Hakim Ahmed presently working as a Deputy Head of the Department of Mathematics, University College of Al Qunfuda, Saudi Arabia. He has 15 years of experience of teaching and 10 years of experience in research. He has published many research papers in the field of fuzzy sets and fuzzy topology in reputed international journals. And also he has presented many papers in various international conferences held at India, Greece, Turkey, and Egypt. He is acting as a member of various committees in his college. Particularly, he is working as Assistant Vice Dean for Quality and Development in this college. He has reviewed many PhD theses and research papers, various authors from different countries. Dr. Hakim has attended more than 15 training programs and workshops. He is life member of various professional bodies, in particular American Mathematical Society. Also, he has been acting as a member of editorial board of 3 international journals. On this occasion, it is my honor to state that he has received Junior Research Fellowship to foreign student from University Grand Commission, India in the year 2008. So hence, I invite our resource person, Professor Dr. Hakim, to deliver a talk on a new nano operator for a new nano topology. So thank you all. Thank you.
Thank you, sir. Thank you. Shall I start?
Now I request Hakim sir to take over the session.
Okay. It's clear for you now, the presentation?
No, sir, the screen is not visible, sir. Sir, now it's visible.
Visible. Okay. First of all, I want to thank the organized committee of the conference and all staff of PG and Research Department of Mathematics, Punkanado Arts and Science College. And I want to thank also everyone who participated in this international seminar. I am so happy to be with you, and I am so proud to be with the king of topology, Professor Said Jafari and Professor Benchel. My lecture will be in new nano operator for new nano topology. In this presentation, I will use a nano G-open subset of nano topological space to introduce two nano operator called nano H closure and nano H interior. Using nano H interior, we shall define a new nano topological space, namely nano H topological space. Moreover, we shall discuss and examine the fundamental properties of this new nano operator and new nano topological space, with emphasis on the transfer of nano regular space condition on nano topological space to nano separation axiom condition on nano H topological space. Some application will be investigated. Introduction. The notion of your closed set was introduced in 1970 by Levin. In 2030 by Pittiger and Carmel introduced the nano-topological space and nano-continuous mapping, beside on the concept of lower approximation and upper approximation and boundary. Some papers such as 3 and 1 show that the concept of nano-topology can be used as a tool to study certain real-life problems. Now we'll start. A boundary region of X with respect to R, where an X is a subset of U. Then that topology, nano-topology, satisfies the following condition. Phi and U belong to nano-topological space, and the finite intersection of elements of nano-topological space is in nano-topological space. The union of any element of nano-topological space will be in nano-topological space. You can see it is like the definition of the general topology. Any element of nano-topological space are called nano-open set. The complement of it are called the nano-closed set. Also, you'll see here the definition of some famous set in nano-topology, nano-generalized closed set, nano-alpha open set, nano-beta open set, nano-semi open set, nano-beta open set. And it's like the definition in general topology, but use the nano-interior or nano-closure. Here also the definition of some continuous mapping. Nano-continuous if the inverse image of its nano-open is nano-open. Nano-pre-continuous if the inverse image of nano-open set is nano-pre-open set. Nano-semi-continuous if the inverse image of nano-open set is semi-open set. And nano-alpha continuous if the inverse image of each nano-open set is nano-alpha open set. Also have the definition of the separation axiom in nano-topological space, nano T0 and nano T1, nano T2, and it's like the definition of general topology, but we use nano-open set, nano-regular space, nano T3, nano-normal, nano T4. Now we shall start the some result in this presentation. We define now the new nano operator, new operator. Nano H closure of lambda is equal the intersection of all nano G open such that lambda subset of mu is called nano H closure. Nano H interior of lambda equals the union of all nano G open such that mu, the nano G open is subset of lambda. Now we'll introduce a new nano topology generated by the new operator nano H interior. Let we have nano topological space. The new nano topological space generated by nano H interior, that is, we can define it by this H nano topological space equal to lambda subset to U such that nano H interior equal of lambda equal lambda. The member of all H nano topological space is called nano H open set. The complete of H is called nano H closed set. And the family of all nano H open set we can denote it by this, and also the family of nano H closed set we can denote it by this notation. Here we will get the difference. This remark: the member of H nano topological space are closed under the intersection property, and the complete of nano H topological space are closed under the union property. The union of member of H nano topological space is not need to be a member of nano H topological space in general. The intersection of member of the complement of nano H topological space is not need to be member of nano H the complete of nano H topological space in general. You can see the nano topological space is a subset of nano H topological space, and also the complement of nano topological space subset of nano H topological space. There is some example. I introduce some example that clarify that above remark. There is some example for that. Also, we have this remark: for any subset of U, nano topological space and nano H topological space, we can see this remark: nano closure. The nano closure is nano closed in nano topological space, but the nano closure, the nano H closure, is not need to be nano H closed in general in nano H topological space. The nano interior is nano open set in nano topological space, but the nano H interior is not to be need to be nano H open set in general in nano H topological space. Also, we have some example to clarify this thing. Now we'll start by some interesting theorem. For any nano topological space and X belong to U, either singleton X is nano H open set, or the complement of singleton X is nano open set. This is the proposition for from this theorem. For any nano topological space and X belong to U, either the singleton X is nano closed set, or the complement of the singleton X is nano H closed set. So we can also get this this theorem. If you have a nano topological space, then the following statements are equivalent. If nanotopological space is nano T half space, the second statement, every singleton in nanotopological space is either nano-open set or nano-closed set. Every subset of U is the intersection of all nano-open set and all nano-closed set contained in it. This also remark they will give you a relation between nano interior or nano X interior. See, if you have nanotopological space and lambda subset of U, then we can know that nano open set is nano H open set. And if lambda subset of U, then the nano interior lambda subset of nano H interior lambda subset of lambda. Nano closed set is nano H closed set. And if we have lambda subset of U, then lambda subset of nano H closure of lambda subset of nano closure lambda. Also, we have some examples where they give you the comparison of that relation is not true. Also, we have here some interesting theorem. If you have the nanotopological space is nano T half space, if and only if the nanotopological space subset of nano X topological space would equal. For any nanotopological space and X not equal Y, then nano H closure of X not equal nano H closure of Y. For any nano H topological space is nano T0 space. Now we can get interesting theorem. If any space is nano topological space and nano H topological space, then it is nano half space. If a nano topological space is nano regular space, then the nano H topological space is nano T3 space. That means nano regular space and nano T1 space. Shall we define now the R0 space? A nano topological space is said to be nano R0 space if the singleton R nano H closed. Now we can start by this theorem. If nanotopological space is a nano R0 space, then the nano H topological space is nano T1 space. Remark, the strong theorem in nano T1 space is failed in nano H topological space. That is, the nano topological space is nano T1 if and only if every singleton is nano closed set. There's also one example. It's clarifying this remark. Now we can replace that theory. If you have nano H topological space is nano T1 space if and only if every singleton is nano H open space for all X belong to you. I can also introduce this interesting theorem. Let we have a nano topological space, then the following statements are equivalent. Nano topological space is nano T1 space. For every X belong to you, every singleton is nano H open set. For all X belong to you, the drive our limit point of singleton of X equal to 5. This is the figure that most result in this figure about the transfer property from nano topological space to nano H topological space can be summarized by the following figure. So you can see that all how you can transfer the relation between nano topological space and nano X topological space with nano separation axis. By the nano operator, nano H interior, I introduce all this new set in nano H topological space, and future work need to be done on this set. So let you nano topological nano H topological. This is we have to put not H topological, nano H topological space, and the set new subset of U is called nano H alpha open F lambda subset of nano H interior, nano H closure, nano H nano closure, nano H interior. So this is the nano topological space. Nano H pre-open F the lambda F the mu subset of nano H interior, nano closure. Nano H semi-open F mu subset of nano closure, nano H interior mu. Nano H, now we define nano H beta open F the mu subset of nano closure, nano H interior, nano closure mu. This is the relation between all the set. We can see the relation between the set in nano topology and nano H topology. Also, we give some example. We have some examples that clarify the comparison. The comparison of this relation is not true in general. So also we define some mapping in nano H mapping. Nano H mapping. If the inverse image of nano H open is nano H open. Nano H pre-continuous if the inverse image of nano H open is nano H pre-open. Nano H semi-continuous if the inverse image of nano H open, nano H semi-open. Nano H alpha continuous if the inverse image of H nano H open is nano H alpha open. This is the some reference I have to use it. Thank you for attention, and this is my idea of connection. If anyone want to connect a connection with me. Thank you to all. Hello, sir.
Hello, sir.
Finished.
Okay, sir. Thank you, sir. Thank you, sir. Sir, thank you. Thank you so much. It was a wonderful session, and you have shared the operators on nano topology. Sir.
Thank you, madam.
So thank you so much, sir. We would like to have you in person in future and upcoming seminars or conferences. We would like to get connected with you, sir. Sir?
It is my pleasure. It is my pleasure to do that.
Thank you. Thank you so much for accepting our invitation and for being with us today, sir. Thank you.
I am happy and proud. I'm happy and proud of that.
Let's go in for the next session. Every thought you produce, anything you say, Any action you do, it bears your signature. Benchali sir, ಈ ಸೆಮಿನಾರ್ಗೆ ಸ್ವಾಗತ.
Yes, tell me, madam, tell me.
ಈ ಸೆಮಿನಾರ್ಗೆ ಸ್ವಾಗತ ಸರ್.
Thank you, madam. Thank you. Very, very happy.
Yeah, we are very happy. We are very much happy to meet you once again for you being with us for the second time too, sir.
Yes, madam. Thank you. Thank you.
Thank you so much for being with us today, sir. I now invite Dr. S.P.R. Priyalata to give a glimpse of introduction about our chief guest of next session. Priyalata, over to you.
Thank you, madam. Good afternoon to one and all. It's my great pleasure to introduce our resource person, Dr. S.S. Benchali, sir, retired professor, Department of Mathematics, Karnataka University, Dharwad. He started his research work in topology in 1976, worked with Professor S.R. Malhan for his doctoral degree. He received UGC fellowship to pursue his PhD degree in mathematics. He has more than 35 years of teaching experience. His research interests are in the field of fuzzy state, fuzzy topology, fuzzy logic, general topology, dimension theory, and bitopology. He has successfully guided 14 students for their PhD degree and 25 students for their MPhil degree. He has published more than 70 research papers in national and international journals. He is working as coordinator of UGC Special Assistance Program of the Department of Mathematics from the year 2008. During his academic career, he has attended more than 50 national and international conferences and seminars organized in various parts of the country. He visited many universities in USA like University of Chicago, University of South Florida, and Florida Institute of Technology. He is a member of many professional bodies like Indian Mathematical Society, Ramanujan Mathematical Society, and Kerala Mathematical Association. He is a reviewer of American Mathematical Society's Mathematical Review and referee for many national and international mathematics journals. Once again, I welcome you, sir, to deliver the talk on recent trends in topology. Sir, please.
Thank you, madam. Thank you for the kind introduction. Thank you. Shall I share the screen?
Yes, sir. Sure.
Is it visible, madam?
Yes, sir. Yes, sir. It's visible.
Can you see the slides?
Yeah. We can see, sir. It's visible.
Oh, everything is all right?
Yeah. It's all right, sir. You can continue. You can proceed.
Yes, ma'am. Thank you. Thank you. Thank you. So it gives me a great pleasure for me to participate in this international program, international virtual conference on topology and its applications, right? And I'm very much thankful to the organizers for giving me this opportunity. Okay. The topic that I have chosen for today's lecture is recent trends in topology. And I will try to deal with these things during the next 1 hour or so. I will be dealing with general topology, an introduction, and then objectives of general topology, topology and its origin, historical emergence of topology, emerging trends in topology, non-continuous functions, and then concluding remarks. And during my presentation, I will try to put the things in very simple terms so that everybody can understand the ideas. So general topology and introduction, the first item. Under this, I would like to deal with topological spaces, open sets, closed sets, examples of topological spaces, number of topologies as an open problem, continuous functions in topology, continuous functions on the real line, and equivalence. So first thing, topological spaces, open sets, and closed sets. Now I will begin with the definition of a topological space, which everybody knows, everybody who is working in the area of topology and related areas. You are all familiar with the definition of a topological space, but yet I will begin with this definition, basic definition. And let tau be a family of subsets of X satisfying the following axioms. If tau satisfies the following axioms, then we call it a topology on X. What are the axioms? X and phi, they are members of tau. Union of members of tau is again a member of tau. Intersection of finitely many members of tau is again a member of tau. In other words, if tau is closed under the formation of arbitrary unions and finite intersections, then we call tau a topology on X. And the ordered pair X tau is called a topological space. We call X tau, the ordered pair, as a topological space. We may also simply say that X is a topological space without mentioning tau. Members of tau, they are called open sets or tau open sets. So therefore, we have definition of an open set as follows. Let X tau be a topological space. A subset U of X is said to be an open set or tau open set if and only if U is a member of tau. So the members of tau, they are called open sets. We have the following basic properties of open sets. In
Sir?
any topological, yes, please, madam.
Sir, slide is not moving, sir.
Slide is no. I'm dealing with the first slide only.
Oh, okay, sir. Okay, sir. The participants are saying that the screen is not visible. That's right.
No, I'm just dealing with the first slide only.
Okay, sir. No issues, sir. Thank you, sir.
I'm explaining each and everything in the first slide only. Okay.
Okay, sir. No problem, sir.
Right. I will continue.
Okay, sir.
So I'm trying to explain the topological spaces, the basic ideas, open sets, closed sets, and the related things. Right. So X and phi, they are always open sets. Union of open sets is again an open set. Finite intersection of open sets is again an open set. Then examples of topological spaces, the second item in this slide. So if you take any set X equal to, say for example, X equal to ABC, then let tau1 be equal to X and phi, set containing a family containing X and phi, then it is a topology on X. Then second family tau2 equal to, say for example, X phi singleton A, that is also a topological space. That is also a topology on X. If you take tau3 is equal to X phi singleton A and then BC, then that is also a topology on X. If you take tau4 is equal to the family of all subsets of X, then it is also a topology on X. These are few examples of topologies on the same set X. Then suppose you take a family containing X, phi, singleton A, and then singleton B. Then it is not a topology on X. Another family consisting of X, singleton A, singleton C, and then AC. It is also not a topology on X. So from these examples, it is clear that every set can be made a topological space. You take any set X, it can be made or it can be viewed as a topological space. That's the first observation. Then second observation is, there can be many topologies on the same set X. The same set X can be made a topological space in many ways. Then another observation, not all the families of subsets of X can be topologies. You just take any family, it is not that it is a topology on X. It can be a topology on X or it may not be a topology on X. Then another example, let X be any set and let D be equal to the power set of X, that's the family of all subsets of X. Then it is a topology on X. And this topology is called discrete topology on X. And in any discrete space, every subset of X is an open set. Another example, let X be any set and consider the family consisting of only X and phi. Then this family is a topology on X. And this topology is called the indiscrete topology on X. And in the indiscrete topology, the only subsets of X, namely X and phi, they are the open sets and no other subset is open. Another example, let X be equal to the set consisting of 2 points 0 and 1. And let S be equal to X family consisting of X phi singleton 0. Then S is a topology on X. And this space, XS, is called Sierpinski space. Then we move to the next point, that is number of topologies, an open problem. Let X be any set containing n distinct points. Let T of n denote the number of distinct topologies on X. Then it is found that T of 1 is equal to 1. That is, on a set consisting of 1 point, we can construct one topology. T of T2 is equal to 4. That is, on a set consisting of 2 points, we can construct 4 distinct topologies. For example, if you take capital X equal to small a and small b, 2 points, then on that set, you can construct 4 topologies. Then T of 3 is equal to 29. If capital X equal to, say for example, set consisting of A, B, C, 3 points, then we can construct 29 distinct topologies on X. Then T of 4 is equal to 355. Interestingly, you see that if X equal to A, B, C, D, 4 points, then one can construct 355 distinct topologies on X. That means that X equal to ABCD can be viewed as a topological space in 355 different ways. Then you see the next jump from 4 to 5. If you take a set consisting of 5 points, then you can construct 6,942 topologies. That means the same set X can be viewed as a topological space in 6,942 different ways. Let us go to the next step. Let me take a set consisting of 6 points. Then one can construct 209,527 different topologies. 209,527 different topologies on that set. The next jump you just see, if you take a set consisting of 7 points, then one can construct 95,35,241 topologies, different topologies on that set. I repeat, on a set consisting of 7 points, 95,35,241 topologies can be constructed. For more details on this, one can refer to the book by A. Wilansky, Topology for Analysis. And it is observed that there is no general formula for T of n. There is no general formula for the number of topologies on X consisting of n points. So this is about the number of topologies, an open problem. Now, regarding the topologies and examples of topologies, I told you that every set can be made a topological space. Now, let me take the set of all real numbers, the real line. Now, we can construct many topologies on R. That is, the real line can be viewed as a topological space in many ways. For example, R can be viewed as a discrete space. You take all the possible subsets of R, it is a topology on R. Another way is you can construct indiscrete topology on R. That is, if you consider the family consisting of R and phi, then it is a topology and it is the indiscrete topology on R. That means R can be viewed as an indiscrete space. Another example is, if you take the family consisting of R, phi, and singleton 0, that is also a topology on R. Another example, R, phi, singleton 0.5 is also a topology on R. So therefore, R can be viewed as a topological space in many ways. But however, we are interested in one particular way of making R a topological space, and that particular way is called standard topology on R, or the Euclidean topology on R, or the usual topology on R, or the one-dimensional Euclidean topology on R. And the definition of such a topology is, we are all familiar with this, U equal to set of all G subsets of R such that for every X belonging to G, there exists a real number R greater than 0 such that the open interval X minus R to X plus R is contained in G. This family together with empty set. This family, one can verify that forms a topology on R. And along with this topology, R becomes a topological space. And this topological space is called the standard topological space, or the Euclidean topological space, or the usual topological space, or the one-dimensional Euclidean topological space. And whenever we refer to R as a topological space, it is always understood that it is this topology that is associated with R. Even without mentioning, it's always understood that on R, we are referring to this particular topology. So this is regarding the R as a topological space. Now we have the following remarks regarding the real line with the usual topology. Every open interval in R is an open set in R. Which are the open sets in the real line with the usual topology? So every open interval is an open set. Union of open intervals in R is an open set in R. And the converse of the first observation is not true in general. That is, an open set in R need not be an open interval in R. And for example, if you consider the open interval 0, 1, union the open interval 2 to 3. So this is an open set in RU, real line with the usual topology. but it is not an open interval in R. So that justifies that the converse of the first observation is not true in general. Then moving on to the next example, you take the set of all natural numbers, n equal to 1, 2, 3, 4, 5, and so on. Then on n, you can construct many topologies. N can be viewed as a discrete topological space. N can be viewed as an indiscrete topological space, and so on and so forth. So the natural numbers can be viewed as a topological space in many ways. Now we have the definition of closed sets in topology. Let X tau be a topological space. A subset A of X is said to be closed or closed in X or tau closed in X if and only if its complement X minus A is an open set in X, or equivalently X minus A belongs to tau. Observation, immediate observation, the complement of an open set is always a closed set and vice versa. So one is the complement of the other. So open sets and closed sets, they play a very important role in topology, in the study of topology and the topological spaces and the related ideas. Then we have immediate properties of closed sets. The first observation, the first property, X and phi, they're always closed sets. Second, arbitrary intersection of closed sets is always a closed set. Third, finite union of closed sets is always a closed set. These are the three basic properties of closed sets. So combining the properties of open set and closed sets, we have this observation. In any topological space, we have open sets, we have closed sets, we have open sets but not closed sets, we have closed set but not open, we have both open and closed sets, and we may have neither open nor closed sets. All these possibilities are there. Now we move on to continuous functions in topology. Now let me define continuity in topological spaces as follows. Let X tau and Y tau star be any two topological spaces. Then consider a function f from X to Y. It is said to be continuous if the inverse image of each open set in Y is open in X. So f is a function from X to Y, and it is any open set in Y, its inverse image, f inverse of U, must be open in X. In other words, for every U belonging to tau star, f inverse of U should belong to tau. If this is satisfied, then the function f from X to Y is said to be a continuous function. Now observe that the definition of a continuous function is in terms of open sets. Then examples of continuous functions. Every constant function is always a continuous function. One can verify this easily. Then another interesting example of continuous functions. Let X be any discrete space and Y be any topological space. Then every function from X into Y is continuous. See, the interesting thing is, if you take X, the domain space, any discrete space, and Y, any topological space, then every function from X to Y is continuous. You define the function from X to Y in any way you want, then the function becomes a continuous function. Now the reason is, you take any open set in Y, then you take its inverse image, F inverse, and because the domain space is a discrete space, and because every subset of X is open, then the F inverse of that open set becomes an open set, justifying or satisfying the definition of continuity of the function. So therefore, f becomes a continuous function. Another interesting example, let X be any topological space. Now the domain space X be any topological space and Y be any indiscrete space. Then every function from X into Y is continuous. So again, to justify this, because Y is an indiscrete space, the open sets are only phi and X. Now you take phi and you take the inverse image of phi. F inverse of phi is phi and phi is open in X because in the domain space X, because it is a topological space, X and phi, they are always open sets. So phi is open. Now take the second open set, namely Y, and take its inverse image, F inverse of Y. F inverse of Y is nothing but X and X is open in X. So therefore, inverse image of every open set in Y is open in X and therefore F is a continuous function. First one is the composition of any two continuous functions is again a continuous function. Second, the restriction of a continuous function to a subset of the domain is again a continuous function. F restricted to A, for example. The third, if F from X to Y is a continuous function, then F from X to Fx is also a continuous map. That is, the restriction to the range is also a continuous function. These are the three basic properties of continuous functions. Then a characterization of a continuous function. What do I mean by a characterization? By a characterization of a particular idea, a particular definition, a particular concept, in topology, means any other statement which is equivalent to the given idea. So that's what we mean by a characterization. Now, characterization is generally described by other ideas. For example, in case of continuous functions, the definition of continuous functions is in terms of open sets. Now, the definition W in R containing f of x naught, there exists an open set phi in R containing x naught such that f of v is contained in W. This follows from the previous characterization of a continuity of a function. Now, from all these things, we have R is associated with the usual topology. In other words, when f is a function from R to R, then there are two definitions of continuity. One definition is inverse image of each open set in R is open in R. That is the topology definition. Another definition is the epsilon delta definition. And what conclusion we have come is that both these definitions are one and the same. That is, both these definitions are equivalent. This motivates to take the definition of continuity to more general spaces. That is, when from f from x to y, where x and y are any two topological spaces. So this is regarding the this slide. We move on to the next slide. The objectives of general topology. So here, we would like to know what are the things that we study in general topology. I will just go through these things quickly, which we all of us we know. In general topology, we study the following things. Topological spaces we study, open sets and closed sets. And then elementary concepts we study, the closure, the interior, the boundary of every subset of a topological space. Then we study bases, we study sub-bases, dense sets, neighborhoods. Then Kuratowski's closure operator. Subspaces we study maps, that is functions. We study continuous functions, we study open maps, we study closed maps, homeomorphisms, we study topological property, we study connectedness, local connectedness, path connectedness of spaces, we study compactness, locally compact spaces, limit point compact spaces, sequential compact spaces, countable compact spaces. Then we study separation axioms like T0, T1, T2, that is Hausdorff spaces, regular spaces. We study T3 spaces, normal spaces, T4 spaces, completely regular spaces, Tikhonov spaces, completely normal spaces, countability axioms, that we study first countable spaces, second countable spaces, Lindelof spaces, separable spaces. We study convergence in topology, convergence of sequences, subsequences, sequential compactness. We study compactification, one-point compactification, Wallmann's compactification, stone-check compactification. Then we study metric spaces, we study nets and filters, we study paracompact spaces. So the objectives continued. Along with these things, we also study the interrelations. What do I mean by interrelations? For example, you have T2 spaces and you have T1 spaces. What is the interrelations between T2 space and T1 space? For example, every T2 space is a T1 space. Another example is, so we study connectedness and compactness. What is the interrelationship between connectedness and compactness? Is every connected space compact? Is every compact space connected? And so on and so forth. So whenever we introduce or study a particular property and another property, then we would like to know the interrelations. So this is one of the aspects that we deal with in topology. The next is characterizations. Just a while ago, I explained the characterization of continuity. Now, as I told you earlier, by a characterization we mean, given an idea, say for example, in terms of open sets, we would like to give equivalent statement or statements in terms of some other ideas. For example, in terms of closed sets, it may be in terms of closure, it may be in terms of interior, it may be in terms of convergence of sequences, it may be in terms of neighborhoods, and so on and so forth. So such things, they are called characterizations. And characterizations are required to know fully the topological spaces or that particular concept. To give you one or two examples of characterizations, already we had characterizations of continuity. Another famous characterizations is Urizone's characterization of normality. When you study normal spaces, then you study Urizone's characterization of normality. A topological space X is normal if and only if there exists a function f from x to 0, 1, such that a continuous function such that for every pair of disjoint closed sets, one closed set goes to 0, another closed set goes to 1. So this is a very nice characterization, and it characterizes normality in terms of existence of continuous functions. So therefore, this is regarded as a bridge between topology and analysis. So characterizations are a part and parcel of the study of general topological spaces. And then we have hereditary properties. What do I mean by a hereditary property? Suppose X is a topological space, and we talk of subspaces. So what do I mean by a subspace? Given a topological space, given a subset of it, say Y, a subset of X, then can you make Y a topological space? Yes, we can make Y a topological space, again in many ways. But we are not interested in all those ways. We are interested to make Y a topological space in a particular way. That particular way is called relativization or subspace topology. So Y along with the subspace topology is called subspace of that main space X, right? So coming to hereditary properties, given a topological space X, and you take a Y, a subspace of X with relative topology, then the question is whether Y also has that property. For example, if X is a T2 space and if Y is a subspace of X, the question is Y also a T2? Whether every subspace of a T2 space is T2. So such questions are asked. So whenever we study a particular property. So this we do with regard to normality, with regard to regularity, with regard to T2 spaces, with regard to T1 spaces, and so on and so forth. In some cases, every subspace may have the property. In some other cases, every closed subspace may have the property. In some other cases, every open subspace may have the property, and so on and so forth. So we try to investigate these properties, such properties under hereditary properties. The next one is topological invariance. So what do I mean by this? By topological invariance, we mean whenever we have a function f from x to y, and whenever x has some particular property, say for example connectedness, then under what conditions y also has the property. If y also has the property, connectedness, then we say that the connectedness is a topological invariant. And to get to this, we would like to study, we would like to know what are the conditions required on the function f. Whether continuity is enough, or continuity and open is enough, continuity and onto is required, continuity and bisectivity is required, and homeomorphism is required, and so on and so forth. right? Now, for example, we know that continuous image of a connected space is connected, right? Connectedness is invariant under continuous maps. So such things we would like to study in topology with respect to every property that we study, whether it is a T1 space, whether it is a T0 space, whether it is a Hausdorff space, whether it is a regular space, normal space, connectedness, compactness, paracompactness, first countability, second countability, and so on and so forth. For every property, we would like to study the topological invariance. Then the next interesting thing is product invariance. I will explain a little bit about the product space. Given any two sets X and Y, we are aware of the Cartesian product set X cross Y. The Cartesian product set X cross Y is equal to the set of all order pairs A comma B, where A comes from X and B comes from Y. So this is an ordinary set theory. Now, coming to topology, suppose X is a topological space, Y is another topological space. Then consider the Cartesian product set X cross Y, right? Now we would like to consider X cross Y as a topological space. We would like to weave the Cartesian product set X cross Y as a topological space. Now again, we know that every set can be weaved as a topological space in many ways. Therefore, the Cartesian product set X cross Y can be viewed as a topological space in many ways, right? For example, it can be viewed as a indiscrete space. It can be viewed as a discrete space, and so on and so forth. But we are not interested in all these varieties of topologies on X cross Y. We are interested in viewing the Cartesian product set X cross Y as a topological space in a particular way. That particular way is called the product set, the product topology. So along with product topology, the X cross Y now becomes a product space, right? If at all you want to, you want me to go and define the product space, now you take an open set in X, another open set in Y, so form U cross V and form all such, and then it will generate a topology on X cross Y. That is a topology for which this family is a basis, right? So this topology is called product topology on the set X cross Y, and the set X cross Y along with this product topology is called the product space X cross Y. Now, coming to this particular point, product invariance, what do I mean by this is, when X, a topological space X has a particular property, another topological space Y has the same property, right? Then the question is whether the product space X cross Y also has the same property. For example, if X is a T2 space, Hausdorff space, Y is also a Hausdorff space, then what about X cross Y? Is it also Hausdorff? If it is so, then we say that Hausdorff property is product invariant. It doesn't change under the formation of the product. So the example is the same. Example satisfying the particular, this T2 is satisfied. Right? That is, if X is T2, Y is T2, X cross Y is T2. And we also deal with the converse. If X cross Y is T2, what about the individual spaces? Are they T2? Right? In terms of compactness, in terms of connectedness, if X is compact, Y is compact, what about X cross Y? If X is connected, Y is connected, what about X cross Y? If X cross Y is compact, what about each space X and Y? If X is paracompact, Y is paracompact, what about X cross Y? Is it paracompact? Conversely, if X cross Y is paracompact, what about X, what about Y, and so on and so forth. So all these things with respect to all separation axioms, countability axioms, and so on and so forth, the product invariant properties, so we study in general topology. The next one is examples and counterexamples. So in topology, whenever we introduce a particular thing, it may be a T0 space, it may be T1 space, it may be T2 space, it may be regularity, it may be normality, and so on. We have to give examples. We have to justify with the help of examples. That means we have to show that there are enough topological spaces which satisfy that particular idea, that particular concept. For example, whenever I define a Hausdorff space, I have to give an example of a Hausdorff space. So plenty of examples of Hausdorff spaces. Similarly, I have to also give counter examples. That means an example of a topological space which is not Hausdorff, an example of a topological space which is not compact, an example of a topological space which is not connected, an example of a topological space which is not paracompact, and so on and so forth. So therefore, ideas have to be justified with the help of examples and counterexamples. Okay, shall go to the next slide. Now, topology and its origin. So, what is the origin of topology? Topology grew from which ideas and which field? Any student of calculus, the first line is the real line properties and calculus on the real line. Like algebra, geometry, and analysis, topology, topology is also a branch of mathematics. Any student of calculus is exposed to continuous functions, that is, continuous functions from R to R, which plays a fundamental role in calculus. Now, the idea of continuity involves the idea of limit, which in turn involves the concept of nearness. Calculus students are also familiar with the idea of an open interval. An open interval, in terms of nearness, is just a set which, when it contains a particular point, also contains all points sufficiently near to it. Topology is that area of mathematics which takes on the concepts of nearness, the concept of limit, the concept of limit point, the concept of continuity, etc., to more general sets and gives them their most general, meaningful, rigorous definitions and studies the consequences. In other words, topology is said to be the study of nearness. Hence, the concept of topology has roots in analysis, particularly real analysis. Therefore, topology grew out of the study of the real line and the Euclidean space and the study of continuous functions on these spaces. So that means topology has roots in real analysis. Many ideas from the real line and the real analysis, they are taken onto the more abstract sets called more abstract spaces, topological spaces. For example, the idea of continuity from R to R is taken on to the topological spaces from one space to another space. The idea of an open interval is taken on to the topological spaces. The idea of limit point is taken on to the topological spaces. The idea of connectedness in the real line is taken on to the topological spaces. The idea of compactness on the real line is taken on to the topological spaces, and so on and so forth. So the ideas from the real line are taken on to the abstract general topological spaces. So therefore, the topology, the branch general topology mainly, grew from the ideas of general topology. Topology can be subdivided into three branches. One is general topology, or the point set topology, or the set theoretic topology. General topology is also called the point set topology or set theoretic topology. Second is geometric topology or differential topology. Third is algebraic topology or combinatorial topology. I'll just tell one or two sentences about each branch. General topology. This branch deals with the study of space of points in which the concepts of nearness, limit, continuity, etc. are given the most general and meaningful form. It deals with the task of generalizing the concepts of geometric figures for spaces of more than 3 dimensions and of investigating their topological properties. That is, properties which are invariant under continuous deformations of geometric objects. This generalization induces the introduction of the notion of topological space, which is a fundamental concept pervading all the branches of mathematics. It had impact not only on the investigation of geometry figures in finite dimensions, finite dimensional spaces, but also led to the introduction of infinite dimensional spaces. So topological spaces, their continuous maps, and the study of their general properties have made up the branch general topology. General topology, or the point set topology, or the set theoretic topology, deals with the study of topological spaces, their continuous maps, and the general properties. So this makes up the branch general topology. The second branch is geometric topology or differential topology. In this branch, again, the ideas of nearness and continuity play a fundamental role. But the study shifts towards the consideration of more of geometric objects, such as spheres and balls. Much of the work can be done in the plane and in 3-dimensional spaces. One cannot really study geometric topology without the sound background in general topology. So for the study of geometric topology, sound background of general topology is required. Geometric topologists normally wants to know the conditions under which two objects, X and Y, are equivalent. A topologist regards two objects as being topologically equivalent or homeomorphic if one object can be made to coincide with the other by means of a motion that may include stretching, twisting, pulling, shrinking, bending, etc. In fact, almost anything except cutting or tearing and sewing together. It should be noted that all the ingredients of such a motion are continuous, and such a motion takes nearby points to nearby points. Cutting and tearing are excluded because they lead to discontinuity. Here, a geometric object is thought of being made up of rubber. Therefore, sometimes topology is also called as rubber sheet geometry. So this is about the geometric topology or the differential topology. And the third branch is algebraic topology. The research work carried out by Henri Poincaré, the great French mathematician of 19th century, is the starting point of algebraic topology. Here, the method of investigation is to associate geometric figures using a rule which is common to all the figures with algebraic objects, that is groups and rings, etc., so that certain relationship between the figures correspond to the algebraic relationship between the objects. Studying the properties of algebraic objects sheds light on the properties of geometric figures. The geometric objects constructed by Henri Poincaré are the homology groups and the fundamental group. So these things are about all the three branches of general, all the three branches of topology. And today what we are dealing with in this lecture is regarding general topology. So we shall move to the next slide. Historical emergence of topology. Now, under this, I would like to give a brief history of topological emergence, a history of nearly 300 years. So I'll start with the Isaac Newton's work. Isaac Newton, whose period is 1642 to 1727, and Leibniz, they are the inventors of calculus. And then Alembert, D. Alembert, 1717 to 1783, A.L. Cauchy, C.F. Gauss, they gave the precise definition of limit, and they studied tests of convergence of infinite series. Then comes the Bolzano, Cauchy, and they defined continuous functions in the 18th century, 1781 to 1884, Bolzano, and Cauchy, 1784 to 1854. They introduced and studied continuous functions. Then Abel, Dirichlet, Du Bois, Raymond, they studied the convergence of trigonometric series. Next slide. Then Bolzano, Riemann, Weierstrass, they gave the first examples of no-hair differentiable continuous functions. Then Murray, Cantor, Dedekind, they gave the theories of real number system. Theories due to Cantor and Dedekind gave description of topological structure on the real line. So these the researchers mainly, they gave their theories of real number systems, and slowly the idea of topology on the real line took place in the research work of these researchers. Then Cantor, beginning of general topology, his work can be regarded as beginning of general topology, 1845 to 1918. Papers published by him between 1879 and 1884, they contributed tremendously to the general topology. Then the origin of general topology around 1900. So topology is nearly 110 years old branch of mathematics. Cantor is regarded as the father of set theory and topology. Studied extensively set theory, Euclidean spaces, and some fundamental notions of topology. G. Cantor. He also studied some fundamental notions of topology, whose period is at 1845 to 1918. Then Jordan, Henry Poincaré, E. Borel, R. Baer, Henry Lebesgue, they studied further important notions restricted to Euclidean spaces. They were introduced and studied. Then Riemann made an attempt to move from Euclidean spaces to the abstract spaces. So Riemann's work is very, very important and gave a breakthrough. He tried to generalize the things from the Euclidean spaces to the general abstract spaces. A particular idea which existed in the on the real line, how to take it to any arbitrary set. So this work was started by Riemann. Then Asoli, Arzela, Volterra, Hilbert, Fredholm, they studied topological structure on some special sets, such as set of curves, set of functions, set of lines, set of planes, and so on and so forth. So from the real line, they thought of topological structure on the set of curves, on the set of functions, on the set of lines, and on the set of planes, and so on and so forth. And then Freche, 1906, abstract spaces with the topological structure, first defined in 1906 in terms of convergence of six. So Freche gave the first definition of abstract topological space definition in the year 1906, and his definition was in terms of convergence of sequences. Reach in 1907 in terms of accumulation points. So he gave the definition of an abstract topological space in terms of accumulation points in the year 1907. Approaches due to Freche and Reach had some drawbacks. Then Hausdorff, 1914, the first satisfactory definition of topological spaces was proposed in 1914 in terms of neighborhood systems. See, Hausdorff in 1914 gave the first satisfactory definition of an abstract topological space. Given any set, when do we call it a topological space? Was first proposed in 1914, and he proposed it in terms of neighborhood systems. And then Moore, R.L. Moore in 1910, another system of axioms for topological spaces in 1910. Then Kuratowski in 1922, the definition of a topological space, which is now generally adopted, was first formulated in 1922 in terms of closure operator. Okay, Kuratowski gave the first satisfactory definition, which today is adopted, and he formulated it in terms of closure operator. So nearly 300 years history of emergence of the notion of topological structure. The word topology literally means the study of surfaces. It is derived from two Greek words, topos, that means surfaces, and logos, that means study. So as we already know, three branches: general topology, geometric topology, and then algebraic topology. Then emerging trends in topology: fuzzy sets, fuzzy logic, and fuzzy topology, rough sets and topology, bitopological spaces, dimension theory and fuzzy topological spaces, soft sets and soft topological spaces, digital topology, and topology is a language of modern mathematics. So this list is not exhaustive. There may be many other emerging trends. For example, neutroscopic topological spaces may also be included in the first one, in the fuzzy topology, and so on and so forth. Then we have a specific illustration on non-continuous function. I think I have another 15 minutes time. I will go up to 5 o'clock. Non-continuous functions. I would like to deal with these things now. Non-continuous functions. The first bullet is weaker form or generalization of continuity. Now, if you take the definition of a continuous function, a function f from x to y is said to be continuous if the inverse image of every open set in y is open in x, and there are several characterizations of continuity and so on and so forth. Later on in the literature, many researchers have studied weaker form or generalization of continuity. Sorry. What do we mean by a weaker form or a generalization of continuity in particular? In general, a weaker form of a particular idea or a generalization of a particular idea. Suppose you have a concept called P and another concept called Q. And if P implies Q, if P gives Q logically, then we call Q a weaker form or generalization of P. For example, you take the idea of continuity and another idea of semi-continuous functions, which was introduced by Jan Levine in the year 1965 by a paper published in American Mathematical Monthly in the year 1965, semi-continuity. And we know that every continuous function is a semi-continuous function. So therefore, semi-continuity is weaker than continuity, or semi-continuity is a weaker form of continuity, or semi-continuity is a generalization of continuity, or semi-continuity may also be called as a non-continuous function, right? So it is well known in general topology that continuous image of a connected. So therefore here, in this situation, I would like to give another, like semi-continuity, another example of a non-continuous function. It is well known in general topology that continuous image of a connected set is connected. We know that if f from x to y is a continuous and onto map, and if x is connected, then y is also connected. Equivalently, if f from x to y is a continuous map, need not be onto, and if A is a connected subset of x, then f of A is a connected subset of y. That is, continuous image of a connected set is connected. Now this is a property of continuous maps. Now this property of continuous maps was used by W.J. Pervin and N. Levine, Norman Levine, in the year 1958. Again, this paper was published in Proceedings of the American Mathematical Society in 1958. And they defined what is called a connected map. New type of maps called connected maps, like semi-continuity, connected maps. And later, several researchers studied connected maps in the literature. We find several papers on connected maps. Then what is the definition of a connected map? A function f from x to y is said to be a connected map if for each connected subset A of x, f of A is a connected subset of y. Here, note that a function f from x, it is simply a function, it need not be a continuous function. A function f from x to y is said to be a connected function or connected map if for each connected subset A of x, f of A is a connected subset of y. Any function which preserves connectedness is called a connected function, a connected map. Then immediate remark, every continuous function is a connected function, but not conversely. Therefore, the concept of connected map is a weaker form or a generalization of continuous map, because continuity implies connectedness of a map. Continuity implies connected map, and connected map is a non-continuity or a weaker form of continuity. It is an example of a non-continuous function. Now, the converse of the above is not true, right? Now, in case of semi-continuity, we know that every continuous function is a semi-continuous function, and the converse is not true. That is, a semi-continuous function need not be a continuous function. So, exactly in a similar fashion, here, connected function, every continuous function is a connected function, but a connected function need not be a continuous function. The converse is not true. This can be justified with the help of an example. Now, the question arises, under what conditions the converse of the above is true? Under what conditions we can get back continuity? That is, under what conditions a connected map becomes a continuous map? The conditions may be on the map, or on the domain space, or on the range space, or both the spaces. These are called conditions implying continuity. Whatever may be the conditions, and whether the conditions are imposed on the function, the conditions are imposed on the domain space, the conditions may be imposed on the range space. So these are called conditions implying continuity. Now, in this connection, several researchers for 15 years, they worked from 1957 to 1972. For 15 years, several researchers worked, and they have given 7 theorems regarding the conditions implying continuity. That is, under what conditions a connected map becomes a continuous map. I would like to mention these results. I am not going into the details of the proofs of these results. I would like to only state the results and emphasize the conditions on the functions and the spaces. The first theorem, if f is a function from x to y is a connected function, if it is an open map means image of each open set is open. Monotone map onto function, and y is semi-locally connected T1 space, then f is a continuous map. So to get back continuity, we need to put these conditions on the function. Basically, it must be a connected map, it must be an open map, it must be a monotone map and it must be an onto map. And on X, we don't impose any condition. And on Y, we impose these conditions. Y must be semi-locally connected and T1. So with these conditions, we get back continuity. F becomes a continuous map. This is one of the results which was proved in 1968. Then theorem 2, if F from X to Y is a connected map, X is locally connected and Y is a space such that F inverse of boundary of N is a closed subspace of X for each N belonging to a base for Y, then F is a continuous map. So again we get back the continuity, and the conditions are F must be a connected map, right? That is the condition on the function. It is a connected map. Yeah, on the domain space X is locally connected. The range space Y must be such that inverse image of boundary of N is a closed subspace of X for each N belonging to a base for Y. So with these conditions, we get back the continuity. This result was proved in 1970. Then theorem number 3, if F is a function from X to Y, is a bi-connected, that is bijective and connected, and F inverse is connected, and Y is semi-locally connected T1 space, then F is a continuous map. So again here, on the function F, we are imposing these conditions. It must be bi-connected. That means the function must be connected map, the inverse function must also be connected, and it must be a bijective map. And conditions on Y must be semi-locally connected T1 space. Then F is a continuous map. Theorem number 4, if F is a function from X to Y, is a bi-connected map, X and Y are locally connected, locally compact, Hausdorff spaces, then F is a continuous map. This theorem was proved in 1970. If F from X to Y is a closed map, X is a regular space, Y is a compact space, and F inverse singleton Y is closed in X for each Y in Y, then F is a continuous map. Theorem number 6, if F from X to Y is a connected map, is a closed map, is a monotone map, X is first countable, regular space, and Y is countably compact T1 space, then F is a continuous map. So to get back continuity, these conditions are required. F is a connected map, it must be a closed map, it must be a monotone map. The domain space X must be first countable, it must be a regular space, and the range space Y must be countably compact T1 space. Under all these circumstances, Y is a continuous map. And this was proved in 1968 again. Theorem number 7, if F from X to Y is a connected map, X is first countable, Y is sequentially compact, Hausdorff space, with the property that the inverse image of every open set in Y is connected in X, then F is a continuous map. So to get back continuity, these conditions are imposed on the function, on the domain space, and on the range space. This was proved in 1972. So these are the 7 theorems which have been proved on connected functions, which is one of the non-continuous functions among several non-continuous functions in the literature. Now note that the above theorems were proved by several researchers during 1957 to 1972, during the span of 15 years. The problem considered is the same in all the above 7 theorems. The problem is the same. Yeah, the problem considered is the same in all the 7 theorems. That is, under what conditions we get back continuity. But the conditions are different from theorem to theorem. That is the beauty of these results. In the literature, several non-continuous functions have been introduced and studied. For example, semi-continuous functions, almost continuous functions, pre-continuous functions, C continuous functions, and so on and so forth. In most of these cases, conditions implying continuity have been investigated. So connected mappings is one among them, and I took the example of connected mappings to illustrate the conditions implying continuity. The study motivates for the several new ideas in the study of non-continuous fuzzy functions in fuzzy topological spaces. So this is all about the non-continuous functions. Then before we concluding remarks, there are many non-continuous functions in general topology, as I mentioned earlier. Then many non-continuous functions in fuzzy topology also. So with regard to all these non-continuous functions, one can study conditions implying continuity. And topology is a language of mathematics. So using this language of mathematics, so many branches of mathematics have been rewritten, can be written in terms of the language of topology. For example, take the complex analysis, the functional analysis, and so on and so forth. All the branches can be viewed through the language of topology. These are the concluding remarks, and I should be thankful to the organizers for giving me this opportunity. I should also be thankful to all the listeners, all the students and teachers, researchers working in the area of general topology or the fuzzy topology or the algebraic topology or the differential topology and so on and so forth. Okay. Thank you one and all. Thank you.
Thank you, sir, for elaborating the concept of topology and its origin and the areas where it can be used. It was a wonderful presentation. It gave the basic knowledge for the young budding researchers. Dear participants, if you have any queries, you can ask now. You can unmute your mic and you can ask the questions.
Any questions?
Dear participants, the feedback link will be available in the chat box only for 10 minutes.
If there are any questions, I am happy to.
Sir, your presentation was so elaborative, and I hope participants, they don't have any doubt. So they haven't posted any questions. So it was a wonderful presentation, and you elaborated it very well. So thank you so much, sir.
Thank you, madam. Thank you.
You have given so much knowledge in depth for the young budding researchers. So it was a wonderful
madam.
session.
Thank you. Thank you. Thank you.
So thank you so much, sir, for being with us today. We would like to have you in person in future.
Ma'am, shall I raise a question?
Yes, Vivek, sir, you can proceed.
Yeah. Thank you so much,
please.
sir. As madam has pointed out, you gave a vivid explanation in each and every aspects of topology. So since we are finding that many budding researchers are over here, so we are finding that in topology, mostly people are defining a set and they are going for certain properties and they are leaving that set as it is. And we are finding there are many sets, newly defined sets, but we are having only few properties discussed. So we are getting more and more sets, but only few properties have been discussed. So how to overcome this? My first question. And second question is, for like we find that corner. It can be implemented at any time. So especially the research aspect has been pointed out. So rather than doing research for the sake of degree, so besides that, doing research with utmost involvement. So what can
Yes.
you, being an experienced research person, so what is the advice you give to the budding researchers? So these are the things which I like to listen from you,
Yeah.
sir.
No. Can you repeat the second part of the question? There was a disturbance in between.
Okay. As actually, now we are around the corner. NEP is around the corner. At any time, it can be implemented. It focuses more on the quality of research. So rather than doing research for the sake of getting a degree, so we expect more of involvement from the researchers in the perspective of quality and
Sure.
research and knowledge.
Sure.
So being an
Sure.
experienced researcher, we would like to listen from you. Your piece of advice will help the budding researchers, sir.
Sure. You have raised a very important question. In fact, two questions. The first question was, many researchers, they try to introduce some idea or ideas, and do some work and leave it there. Okay, that was the first part of the question, isn't it?
Yes, sir. Yes, sir.
So with regard to this, in my opinion, if at all you introduce a new idea, then try to study it exhaustively. Try to study it exhaustively from all the points of views, right? So, for example, try to study all the basic properties, try to study the functions, try to give many examples, many counter examples, try to study the functions from one space to another space with the new idea, try to give the characterizations, try to study the subspace properties, try to study the product spaces, right? Not only finite products, arbitrary products, and so on and so forth. Try to deal with it exhaustively, right? That is in my opinion, one should do it like that. One should not leave it just like that. Just give one or two ideas and leave it there. That is not proper according to me, right? So do it exhaustively and enjoy doing it. And while you go deep and deep into the research work, you will be learning so many things. And degree always comes to you. Degree will not go anywhere. Degree will come to you, but you enjoy whatever you do. You do it with full enjoyment, and you do with full involvement, and go deeply into the subject. You study the subject for the sake of the subject. You try to understand the subject fully, and try to refer, read, understand, and work out as many papers as possible. Try to acquire lot of knowledge in the branch from the books and also from the research work. I would like to give my own example. I worked for 8 years for my PhD. Right from the date of registration till I get the degree, more than 8 years I worked. Right. And I never went to my guide that, sir, whether my work is complete, right? Whether you allow me to submit my thesis. And so I never asked these questions to my guide. I went on working, and my professor also never used to give me the problem, right? He used to tell me, you study the subject thoroughly, right? I used to study the subject thoroughly. And when I was studying, incidentally, I came across with a book called Introduction to the Theory of Fuzzy Subset by A. Kaufman. And the title of the book catched me. I took that book and studied. And the idea of fuzzy subsets was introduced in the year 1965. And I started my work in the year 1976. Right, hardly 10 years of research work in fuzzy sets. and fuzzy topology, hardly few papers had come. Then I started studying fuzzy sets, and I studied that book thoroughly, and I collected the papers on fuzzy topology. I studied on my own, prepared the lecture notes, gave the seminars in front of my teacher and other research scholars, and then I went on like that. I worked for 8 years, and then one day my professor came to my chamber and told me that eventually your work is over, your work is sufficient for PhD. Now you can submit the thesis. So that was the remark from my professor, and then I submitted the thesis. So therefore, my appeal to the young researchers is that get involved in the work, try to understand the subject, and enjoy doing the research work in your particular area. The degree will not go anywhere. The degree will come to you automatically. It has to come to you. But your work is important. You enjoy the work. That is the advice. I think I have satisfied both the parts of the questions.
Yeah, really, sir. Yeah, really, sir. Besides listening to the content what you speak, along with that, listening to the experience what you share, that really matters, sir. So thank you so much. I hope your answer would have ignited the young researchers, and it would have directed, and I hope it will direct the young researchers towards quality research. Thank you so much, sir.
Thank you
so much. Vidya ma'am, over to you.
Now I request Benjali sir to deliver the valedictory address.
Yes, madam. Yes. So after the technical lecture, another duty that is assigned to me is to deliver the valedictory address.
Sir Benjali sir, excuse me for intervening.
Namaste, madam. Namaste, Devi madam. Namaste. Tell me, madam.
Sir, you have given a very nice talk and also very, very simple. And also it is very useful for our young researchers.
Quite elementary, madam. Simple things, simple ideas.
Simple things, from simple things only they can choose topics. One example is, you have given a connected map.
Yes.
Continuous map, everybody knows.
Yes.
But you have introduced a connected map using connected set.
Yes.
Yes, sir.
Yeah. That was the idea of connected maps. Yes, the idea of connected maps was introduced.
It is a weaker form of continuity. Excuse me, sir. Can you hear me?
It was introduced by Parvin and Levine.
Yes, sir. My question is.
Yeah, tell me.
Can the students carry that connected property instead of connected property? Can they use compactness or some other properties? Can we replace the same idea?
Sure. But before that, before that, they have to make the literature survey.
Yes.
What work has already been done?
Yes.
And what has not been done? They have to look into that.
Yes, what you told. That is for nearly 1 year. They have to review this connected map fully. All the papers related to. Then only they can switch on to compact map. Whether we can define a compact map or will it be weaker form like that one. So from your today's speech, many research topics I have observed from your research your speech. There are many 100, 200 research topics are available for our students. If they attended this seminar, this session, definitely they will have a hope. What you told is exactly correct. We will do.
Yes, madam.
And they have to do the new paper.
Yes, ma'am. Thank you, madam. Thank
you.
So
that's one I have observed from your talk. And researchers, it's very, very useful talk for us.
Thank you. Yes, madam.
Very nice talk, sir. And also What I am telling is the students, they can choose topic from your the explanation. Can we,
Yes,
when
madam,
you
yes.
say connectedness, immediately they should think, can we apply
Yes,
this for
yes.
compact set?
Correct,
Can
correct,
it be
correct, correct.
applied? Not like that ones. And
Yes,
usually we have this semi-open and alpha open. These are all weaker forms.
Yes, yes,
But
yes,
you have
yes, madam.
introduced a connected map,
Yes,
which
madam.
is a weaker form, and
Yes.
how to make it. That is, you told that this continuity implies connected map,
Yes.
but connected map can become continuous map if you impose conditions on F or X or Y. That's
Yes.
very, very super explanation, sir.
Yes, madam. Yes, madam.
I should be very much thankful to you, sir.
Thank you, madam.
sir.
I still remember my visit to your college when you were principal. I was there for a Viva.
Yes, sir.
And then also 1 or 2 times I visited.
Yes,
you were not there at that time.
Yes.
And I also remember
sir,
the
yes, sir.
association with Professor Sundaram Pollachi.
Yes, sir. Yes, sir.
Yes.
He is the senior for me in
Yes,
topology.
madam, I know, madam. I know. Yes.
Sir, can we have these in bitopological spaces, this connected map and other things?
Yeah, yes, ma'am. Definitely. When there is an idea, see when
yes.
ideas are there in single topological spaces, definitely they can be taken on to fuzzy topological spaces. They cannot taken on to bitopological spaces. They can also be taken on to fuzzy bitopological spaces, and so on and so forth.
Yes. Okay, sir.
As you have told,
Okay.
there are plenty of ideas the students taken up in many areas.
Yes, sir. That is the spaces, compactness, connectedness, all these properties, they can connect with this topic you have given us, the weaker forms. There are so many weaker forms.
Yes.
How to make that as stronger? By imposing conditions on F, X, Y.
Yes, madam. Yes.
So very nice presentation, sir. Very simple, and also even the student who is studying PG.
Yes.
They can do research now.
Yes.
Simple projects.
Definitely. Simple projects. Yes.
Okay. Sir. Yes, sir.
Thank you.
Thank you so much, sir.
Thank you for your comments. Thank you.
You should come to our college often, and you have to guide our students and staff also.
Definitely, I will come and visit and help them, students.
Yes, the COVID is over. Soon we are expecting you to be in our college.
Yes, madam. Thank you, madam. I will come.
Thank you, sir. Thank you, sir. Thank you.
Thank you, madam. Thank you.
Ma'am, thank you so much for motivating our students to do elaborate work in their research. Thank you, ma'am. Thank you, ma'am. Sir, now I request you to deliver the valedictory address.
Yes, ma'am. Thank you. Now the valedictory address. Good morning to all. It gives me a great pleasure to deliver the valedictory address. This international seminar on topology and its applications was conducted for 2 days. That is today and yesterday, 17th and 18th November. This event was useful to many of the researchers and students working in topology, and even otherwise also. I hope this was useful. We had the opportunity to listen to the lectures by 4 speakers. Dr. Syed Jaffrey from Denmark, with whom we have written some papers, myself and my students. They have collaborated with Professor Jaffrey from Denmark. He spoke on the ideal topological groups. Through his talk, he has inspired many researchers in topology. Dr. M. Parimala, young researcher from Tamil Nadu, India, from Bannariamman Institute of Technology, spoke on neutrophobic topology and its applications. She also illustrated how new ideas from existing ideas can be extended, and she inspired young researchers in the field. Professor Hakim Othman, today from Saudi Arabia, spoke on new nano operators for a new nano topology. He also inspired researchers in general topology. From Karnataka, India, spoke on recent trends in topology and gave an overall picture of research going on in topology and related areas. Though the program was only for 2 days, and earlier it was scheduled for a week, and later on it was reduced to 2 days. And when I asked Dr. Vigneshwaran, he told me some of the constraints from the university and the institution, mainly because of the COVID and the internal assessment tests have to be reorganized. So therefore, the department had to reduce the number of days. So the organizers reduced it to only for 2 days. It was planned systematically and was well organized. The program was well organized. And my personal opinion is that I should have attended the one-week program, but because of the circumstances, it was reduced only to 2 days. Dr. Vigneshwaran told me about the restricting the program only for 2 days from 1 week. Overall, the program was successful and inspiring the young generation to continue to work in topology and related areas. I congratulate all the participants, and I hope that they have been benefited by participating in this program. Long back, I had the opportunity to visit the Kongonadu Arts and Science College, Coimbatore, when Dr. R. Devi Madam was the principal. Here, I would also like to mention that Professor P. Sundaram from Pollachi, NGM College, Pollachi, invited me to Pollachi to attend a conference in the NGM College. That made me to introduce myself to the researchers in topology in Tamil Nadu and Kerala state. I wish the science all the organizers, including the management, the principal of the college, the syndicate member, Vasuki Madam, Dr. Devi Madam, former principal, and Dr. Vigneshwaran, for giving me this wonderful opportunity. I had the opportunity of meeting Dr. Saeed Jaffrey also once again, and also Dr. Hakim through this platform. So thank you, one and all. Thank you. Namaste. Thank you.
Thank you, sir. Thank you so much for mentioning everyone who had took part in this seminar. Your words are very much meaningful to us. So thank you so much. We would like to have been connected with you through collaborative works, through research, and we would like to have in person too. So thank you so much, sir.
Thank you, madam. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you.
Thank you, sir.
The way to develop the best that is in a person is by appreciation and encouragement. I request Dr. P. Satish Mohan, Assistant Professor of Mathematics, to propose vote of thanks. Over to you, Satish, sir.
Yes, ma'am. A pleasant evening to one and all present here. It gives me an immense pleasure to propose a vote of thanks to the International Virtual Seminar on Topology and its Applications, organized by the Department of Mathematics, Kongonadu Arts and Science College, Coimbatore, Tamil Nadu, India. Gratitude opens the door to the power, the wisdom, the creativity of the universe. Today, I take the opportunity to put all my gratitude into words. I thank our most respected Secretary and Director of our college, Dr. C.A. Vasugi Madam, for her great support and inspiration. Thank you, ma'am. I express my sincere thanks to our respected principal, Dr. M. Lakshmanaswamy sir, for his constant support and motivation throughout the year. Thank you, sir. On behalf of the Department of Mathematics and all participants, I would like to express the gratitude to the resource persons of this wonderful seminar, Professor Dr. S. Syed Jafari, Mathematical and Physical Science Foundation, Denmark, Dr. Hakim, Associate Professor, University College of Al Quain Fadak, Saudi Arabia, Dr. Benchali, Professor Retired, Department of Mathematics, Karnataka University, Karnataka, Dr. M. Parimala, Assistant Professor, Department of Mathematics, Bannariamman Institute of Technology, Satyamangalam, Erode, for their great speech and for sharing their vast experience to us. Thank you, professors. I express my sincere gratitude to our Dean Academics, Dean R&D, Chief Executive Officer, Controller of Examinations, IPSC Coordinator, and the librarian of our college for their wholehearted support rendered to us to make this seminar a grand success. It's my duty to thank our beloved head of the department, Dr. V. Gokulavani ma'am, and members of faculty of our department for their untired work. Last but not least, I thank all the participants from various colleges for their active participation to make this seminar a grand success. Thank you all.
Finally, on behalf of the Department of Mathematics, Komunad Arts and Science College, I would like to express my thanks to all the resource persons and appreciation to all the participants for taking time out of their busy duties to attend this seminar. Thank you to all. Jai Hind.